Semiconductor chips, often referred to as microchips or integrated circuits, are the backbone of modern technology. They power virtually all electronic devices and systems. Before chips are manufactured, there is a rigorous chip design cycle with various stages. Out of all stages, the most time-consuming one is design verification. Why is design verification important? Manufacturing semiconductor chips is extremely expensive and time-consuming. Errors detected post-manufacturing lead to massive costs due to scrap, redesign, and refabrication. Design verification involves simulating test cases on design to ensure the chip functions as intended, detecting and correcting design flaws before manufacturing. Many chips are used in mission-critical systems, such as medical devices, aircraft, and automotive safety systems. A faulty chip in such systems can have catastrophic consequences. It is to be noted that for many years now, design verification consumes more than 50% of design cycle time. Thus, I propose using a LLM model to automate generating new test cases. This would greatly reduce the time resource needed to write test cases. This would also create a robust verification suite free from human-prone error. But why Gemini 1.5? Well, the task requires synthesizing information from various types of context. Design files which contains source code defining the SoC architecture. User guide, which contains detailed documentation providing design specifications and usage instructions. Parameters and libraries which contain supporting files containing configurations and reusable components. Test benches and sample test cases which contains existing test setups and examples to guide the generation of new test cases. They collectively form a large corpus of information, totally add up to more than 1 million tokens. Traditional models with shorter context windows would struggle to process and integrate all of this data simultaneously, requiring methods such as vector databases and RAG, which may lead to loss of context. Why vector databases or RAG won't help for this use case? To simplify, they work by retrieving only relevant chunks of data and injecting them to prompt. But the input in our case has logical sequences, highly structured information, and interrelated dependencies between sections. Breaking them into smaller, retrievable chunks loses this continuity. For example, if a test case for the WDT module requires retrieving clock-related parameters, but the retrieval mechanism misses them, the test case might be incomplete or incorrect. Also, there is additional engineering overhead in these methods. Thus, Gemini 1.5's long context window of up to 2 million tokens is perfect, as entire context can be processed in one go, maintaining the logical flow and delivering high-quality outputs without additional engineering effort. For the demonstration I have chosen, Wojian 100% Open, which is an open-source system on chip design developed by T-Head. And I have chosen Gemini 1.5 Flash as the generative model. I have implemented context caching, which is a computational strategy used to improve efficiency by storing and reusing portions of context or data that are repeatedly used in tasks involving generative AI models. Most sections of the input, like user guides, design files, or parameters, remain static and are required repeatedly across multiple prompts. By caching these sections, they are tokenized once and reused across prompts without reloading or recomputing them. This reduces API cost and latency. It also allows for structured management of context, organizing data into key value pairs, making it easy to retrieve or add specific sections. For example, user guide or timer design files when needed. Multi-shot prompting. It involves providing multiple examples of similar tasks or desired outputs in the prompt. These examples act as contextual demonstrations that guide the model to understand the task requirements. With high-quality sample test cases available, I am utilizing multi-shot prompting for this complex task to generate reliable and consistent test cases, leveraging Gemini 1.5's long context window. Providing multiple examples of well-structured verification test cases helps the model learn the generic structure, format, and context in the sample test cases. It helps to identify gaps in existing test cases and extrapolate to cover untested scenarios. Also, there is no need for fine-tuning the model on domain-specific data, saving time and computational resources. The generated test cases not only work as intended, also they are of high quality, complying with best practices. They got test intention, expected output, inline comments, and well-structured. These are important to track test coverage, readability, and for reusability. Say to use them for another project. These are not consistently found in human-created test cases. Thank you for your time.